Welcome, class. Today we are going to start our discussion of Chapter 8. So in Chapter 7, we looked at the chemical equation. We looked at chemical reactions in general. We looked at some types of chemical reactions. And what we want to do now is to take what we've learned about those chemical reactions, more specifically the chemical equations that we use to represent them, and deal with them in a quantitative way, right? So we want to start doing numbers, right? So we're going to reference some of the stuff that we did back in Chapter 6, right? Where we looked at how to quantitatively analyze materials, right? How to figure out how much we have using moles and etc., right? So we're going to, do a similar kind of idea, but now working with an equation instead of just a single substance. So, if we look at the balanced equation, right? So remember in Chapter 7, we talked about how chemical equations had to be balanced. So we have this balanced reaction of octane or gasoline, right? Reacting with oxygen to produce carbon dioxide and water, right? So this is a combustion reaction. Now, what I'm going to point out here is the key thing to quantitatively look at this reaction is to understand what the coefficients are telling us, right? So, just like the mass of an element on the periodic table, right? These coefficients have two meanings, right? We can look at them at an atomic or molecular type level. So we could say 2 molecules of octane react with 25 molecules of O2 to give you 16 molecules of CO2 and 18 molecules of water. But of course, that's not terribly useful for us since we're not going to ever be dealing with 2 molecules of octane. We're going to use these in terms of moles, right? So instead of being 2 molecules of octane, we're going to look at 2 moles of octane molecules reacting with 25 moles of oxygen molecules to give 16 moles of carbon dioxide molecules and 18 moles of water molecules. So the key here is the coefficients give you moles of material. Right. So they are mole based, not mass. Right. So this tells me nothing about the mass, right? I can do that, but in order to do that, I need to convert moles into mass, right? And we learned how to do that back in Chapter 6 using the molar mass. And we're going to bring that into our process here a little bit later. So this whole general study of these numeric relationships between chemicals in a chemical equation and a reaction is called stoichiometry, right? So numeric relations between the chemical quantities in our balanced equation we generally refer to as stoichiometry. And we can do a lot of things, right? We can predict how much product will form in a chemical reaction based on how much reactant we start with. We can predict how much of a reactant is necessary to give me a given amount of product. So I can say, okay, I want to make 10 grams. How many grams of reactant would I need to start with? I have the ability to do that using stoichiometry. And we can predict how much of reactants we need to react with each other. So if I want to react 10 grams of this reactant, how much of this other reactant do I need? Right? And this all goes back to that balanced equation. The coefficients are the key here. So we have to think about a balanced equation as a recipe, right? So they tell us how the reactants combine to form products. So, for example, the recipe to make ammonia is that I need 3 parts hydrogen to 1 part nitrogen to give me 2 parts or 2 ammonias, right? So, the most useful way to think of this is 3 moles of hydrogen react with 1 mole of nitrogen to give me 2 moles of ammonia. That's my recipe. So if I want to make exactly 2 moles of ammonia, I'm going to need to mix 3 moles of hydrogen gas with 1 mole of nitrogen gas. That's the recipe. Now, these coefficients allow me to understand the relationships between the materials in a reaction. So what they tell me is that for every 3 of these, I need 1 of these. Or for every 3 of these, I can make 2 of these, etc. Right? So the balanced equation tells me the relationships. The coefficients, more specifically, tell me the relationships between the reactants and products. So I can set up ratios, right, between any 2 materials. So I know that I have a 3 to 1 to 2 is the overall, so I can make a relationship between any 2 of these. And that's what we're going to do in these problems, right? So in these problems, they're going to tell us we start with this much of this thing, and we want to know something about some other material, right? So there's always 2 things that are involved, what we start with and what we're trying to get to. So for example, if we have 3 moles of N2, more than enough hydrogen, how much NH3 can I make? Now, it's easy to get distracted here by some extraneous information like more than enough hydrogen. The key is, what do we start with? What do we know a quantity of to begin with? And that's the 3 moles of nitrogen, right? So we know something about nitrogen. And what we're ultimately after is how much NH3. So the 2 materials that we're concerned with in this reaction is, if I start with a known amount of N2, how much NH3? So those are the only 2 things that I need to concern myself with. Is I start with N2, I want to get to NH3. So how do I do that? Well, we're going to, of course, use dimensional analysis. And I'm going to start with what I know, 3 moles of N2. And the idea is I want to convert this into moles of NH3. So I need a conversion factor to go from moles of N2 to moles of NH3. And that's where these ratios or these relationships between the coefficients come in, because I know how they're related in this reaction. I know that for every 1 mole of N2, I can make 2 moles of NH3. So there is a 2 to 1 relationship between ammonia and N2, right? And the reason, of course, that I wrote it like this was because I'm starting with N2, I need my N2 on the bottom to cancel. So now it's just a matter of doing the math. 3 times 2 divided by 1, I get 6 moles of NH3. So if I start with 3 moles of N2, I can make 6 moles of NH3 because of this 2 to 1 relationship between the 2 materials. And that's the idea. So by using our coefficients and the relationships between them, I can start with any known amount in the equation and figure out how much of something else in that equation that I can make or that I need to react with, etc. All right, so now we've learned about these mole-to-mole ratios now. These are the key, right? This is the centerpiece to solving these problems, right? This is the new piece, right? Is that these mole-to-mole relationships or mole-to-mole ratios allow us to go from moles of something that we know, say A, and convert it into moles of something we don't know, B. Now, that's useful, but as we looked about back in chapter 6, this becomes really useful when we can put it into mass, right? Because mass is what we can actually measure in a lab. These are the numbers that we need to actually work with. So just like when we dealt with individual materials, while we want to be able to find how many moles there are, right? And if we can know how many moles they are, right? But ultimately, we need to put this in terms of mass, right? And so we can use what we learned in chapter 6 about how to change mass into moles and moles into mass using the molar mass of whatever material we're working with. So we're going to combine this use of mole ratios with our use of molar mass that we learned about back in chapter 6 to be able to start with the mass of some material and convert it into the mass of some other material. So if we're told that we start with this many grams of A and we want to know how many grams of B I can make, well, we can go through this process. And notice it's a 3-step process. We have to convert mass into moles. Then we have to go from moles of what we know to moles of what we don't want to know using our ratio. And then we have to use the molar mass of whatever that material is to get to mass. So 3-step process here. So let's try an example. So we're going to go back to our reaction of octane, right? So we have our balanced equation. So anytime, this is just a good thing to remember, anytime they give you an equation to work with, you always want to double check to make sure it's balanced before you start to do any of these kinds of calculations. So given this balanced equation, I want to know what mass of carbon dioxide is emitted by an automobile per 5 times 10 to the second grams of pure octane used. So the key here is to first identify the materials involved, right? And again, in this type of problem, there's always going to be 2, right? The material we start with, the material we're trying to get to. So in this case, we're starting with how much octane, and we're trying to figure out how much carbon dioxide. So these are the 2 materials that we're interested in. Now, what about all these other materials in the reaction? Well, we don't need to worry about them for this problem, right? If they wanted me to find out how much water was made, well, they could ask me to do that, But all I need to concern myself to solve this problem is the relationship between what I know and what I'm trying to get to. So in this case, between octane and CO2. So if we go back to our process, the first part is to take what we know, in this case the mass, so 5.0 times 10 to the second grams of C8H18, or octane. Now, before I can work with this relationship, right, my 2 moles of octane to give me 16 moles of carbon dioxide, I first have to know how many moles of octane I have. So I have to convert this into moles. In order to do that, of course, I'm going to use the molar mass. Now, what is the molar mass of octane? Well, of course, we need to figure that out. So, if I take octane, the molar mass is going to equal 8 times 12.01 grams per mole for carbon, plus 18 times 1.01 grams per mole for hydrogen. And we're going to put all that together, and it's going to give me the molar mass of 114.3 grams per mole for octane. So I'm going to put that, and of course I need the grams part on the bottom. So 114.3 grams of octane per 1 mole of octane. And so this will convert it into moles. Now I have my moles of octane. Now I can make my switch, right? So now I can go from how many moles of octane to how many moles of carbon dioxide. So that's where this relationship of coefficients comes into play. Now, since I'm trying to find the CO2, that's going to go on top. And my octane's going to go on the bottom. And so I just pull the numbers, right? And again, these are always going to be my coefficients. So 16 CO2 for every 2 octane. So directly from the coefficients 16 and 2, I get my relationships. So this cancels out my moles of octane. So now I know, if I were to solve it now, I would know how many moles of CO2 that I could make. But of course, I want to know this in terms of mass. So I want to convert my moles of CO2 into grams of CO2. And that's going to go back again to my molar mass. And so the molar mass of CO2 is 1 carbon times 12.01 times plus 2 times 16.00 equals 44.01 grams per mole. So 44.01 grams of CO2 per mole of CO2. My moles of CO2 cancel out. So now I can go through and do my math. And so I get to do my calculation. We end up with 1.5 times 10 to the third grams of CO2. Now, of course, notice we didn't ignore significant figures, right? Since we have only 2 significant figures in this original number, then that's how many significant figures I can have in my answer. So 1.5 times 10 to the third, or 1,500 grams of CO2. Okay. So that's the process, right? Now, these can come in all kinds of problems, but the basic process is always the same, right? If we're given a mass of some material and want to figure out how much mass of something else we're going to make or need, we're going to go through this process using our balanced equation. Convert mass of what we know into moles, use the mole ratio of between the material we know and the material we want to find, and then convert that new material into a mass using its molar mass.